Hey guys, so we just went over the really long algebraic way of solving for the equilibrium position for like charges. In doing that math, you can actually find this little equation that I have here for you, and it is something that will determine the equilibrium position for a charge, whether it's positive or negative, of a third bead in between two like charges. So I mentioned it a few times in the last video, and that's that when you have two of the same charges, the bead will always fall somewhere in the center. So the third charge, whether it's positive or negative, will always fall somewhere in the center. So this little equation here that again is derived from the solutions can be used to solve for that position, that equilibrium position, without having to do all of the long algebra. So D in this case stands for the distance between Q1 and Q2. So in this case, it was 4.8, and then A is the origin charge, so the charge for Q1, which for our question was 4, and then B is the second charge, which in our question was 1. And so with questions that give you actual values, let's say like 10 coulombs and 5 coulombs, you would plug in 10 and 5, and if they're negatives, you would just ignore the negative value and plug them in as positives, because if you put in a negative, you're going to get a imaginary number, but it's still going to give you the correct answer. So go ahead and try it for this question. You'll see that you get the same answer, 3.2, and all you really need to do is just plug and chug. But it is derived from the equations. It's not necessarily something I would recommend that you just memorize. Understanding why we use the electrostatic equation and how to cancel out variables and doing algebra is very important. But at this point in the semester, I think that we could all appreciate a few shortcuts. So aside from that, I also want to talk to you about the different scenarios that you can encounter when tackling these problems, and conceptually how you can solve for these conceptual problems that you might encounter. So let me just reduce that. So in this case, we've got two opposite charges. So because we already talked about how if you have two like charges, it's always going to fall in the center, whether it's negative or positive. But here we have two unlike charges, so one positive, one negative, and I chose to make the positive one of a greater magnitude, represented by its size here, greater than the negative charge. So the thing to know with this is that when the charges are not the same, such as you have one positive, one negative, the third charge will be in equilibrium outside of the middle on the opposite end of the larger charge. Doesn't matter whether it's negative or positive, but it's going to be on the opposite end of the larger charge. So if we were to divide this into phases, so phase 1, phase 2, and phase 3, in this case, all of the charges that you put in are going to fall somewhere in phase 3 because it's on the opposite end of the larger charge, in which this case is the positive charge. And I'll demonstrate to you why. So let's start by looking at phase 1. And I'm going to go ahead and erase these. Just keep that in mind, phase 1, 2, and 3. So let's say we put a positive charge in phase 1. Well, that large positive charge is going to have a strong electro-repelling force, and the negative charge is going to have a very small attraction force, but that repulsion force from its same charge, that positive charge, is going to be so strong that it's going to just completely fly it out to the left with a net force, going to accelerate it out of its way. So let's look at the center, which we already discussed is never going to be the case, and I'll show you why. And that's because you're going in both directions. In this case, you have the repelling force to the right and the attraction force to the right, so there's no way that it can balance out. There's no way that it's going to cancel each other out and give you a equilibrium. And then the third position is where we do find the equilibrium, because you would have a small repelling force and a equally large attraction force, because it's now far enough away from the large positive charge to where its repelling force is not going to be so powerful as it was in phase 1, and then it's close enough to the small electric charge that it's now going to have a powerful enough attraction force that it's going to be able to balance out that smaller repulsion force from the positive charge. And so that works the same way with the negative charge. I'll demonstrate that to you very quickly. You have a very large attraction force and a small repelling force here. Doesn't balance out. Whoops. And then if we were to go in the center, you're going to have it in both directions, which is why it's never going to appear in the center for opposite charges. So we would have a attraction force this way and a repelling force this way. No way of balancing that out. And then over here is where we would have a large enough repulsion force this way to balance out an attraction force this way. So notice how whether it was positive or negative doesn't matter. It's really more on which one of these is the larger force is going to determine where it's going to land, and that's always going to be at the opposite end of the stronger charge. And that is for opposite charges, so for positive and negative. If they're like charges, positive, positive, or negative, negative, then it's always going to fall somewhere towards the center. So that's really important to know conceptually, because not all the problems are going to be arithmetic. I know our professor really enjoys to throw in some conceptual problems, because that's when you really know whether you understand a topic or not. Anybody can plug and chug to that little equation that I gave you at the beginning of this video, but to really understand what you're doing and to really prepare for the MCAT material is to understand everything conceptually. So I really hope that helped you guys out, and thanks for watching.